morning, everybody. Today is the 28th of March, and we have begun talking about Chapter 6, which is the Second Law of Thermodynamics. The nuts and bolts of using the Second Law of Thermodynamics as a mathematical relationship comes about in Chapter 7. So in Chapter 6, what we're doing is we're talking about the idea of the Second Law of Thermodynamics. All right, so when we talk about the idea of the Second Law of Thermodynamics, the Second Law of Thermodynamics says a lot of different things, but basically it comes down to this. All real processes occur in a particular direction. And this is involved in a mathematical concept that we're going to introduce in Chapter 7 called entropy. And there are tons of misconceptions and misstatements about entropy. But from an execution point of view, in other words, in terms of doing the Second Law of Thermodynamics, the Second Law of Thermodynamics, which I just often abbreviate 2T, Second Law of Thermodynamics, is the only great mathematical law that is not an equation. We try to make it look like an equation because this makes us uncomfortable. You won't be uncomfortable by the time we finish talking about it, but when you start reading it, it's just like that is just this creepiest thing. Because it's not an equation, because it is not a conservation law. So, in other words, and you may not have even thought about this, but if you give it a moment's thought right now, everything that we've ever done before, we've talked about conserving. We conserve mass, we conserve energy, we conserve, force is equal to mass times acceleration is a type of a conservation law. We're taking one thing and equating it to another. And the Second Law of Thermodynamics is not a conservation law. So what is it? Well, it refers to the idea that all processes occur in a particular direction. So if we think about everyday life, if we think about just living our lives, if I were standing here in front of the room drinking a cup of coffee, what's going to happen to my coffee as I sit here and drink it? Cool down. It's going to cool down, right? What if I have a glass of very cold iced tea and I'm drinking it? What's going to happen to it? Wow. It's going to warm up. How did it know? Why did the heat flow from one direction to the other? Intuitively, why did that happen? Why did my coffee not get hotter? Why did my iced tea not get colder? Because
the universe overpowers the small.
I love that. The universe overpowers the smaller thing. That's exactly right. There is a natural direction for these things to occur. Things that are hot, if you put them in a cooler room, get cooler. Things that are cooler get hotter. Here's another thing. If you're driving in your automobile and you go up a hill, okay? I know this for a fact. I drive a car that gets, on a good day, 30 miles a gallon. When I was driving home from Cheyenne one time, I was driving uphill into a 40-mile-an-hour headwind. Okay, what do you suppose happened to my gas mileage at that point? That's exactly right. It went down to 16. So from 30 to 16. So then if I went around a corner and I was going down a hill and I had a tailwind, am I going to make back that gasoline?
Not necessarily.
Not ever. I'll get better gas mileage, but more gasoline is not going to come into my tank, is it? Right? It's not going to precipitate out of the atmosphere and come into my tank. It will make a difference, but the direction is always still the same. What is the direction? It takes gasoline to run your car. Now, And I always love this. I know this woman who's in her 80s. Her name is Margaret Scranton. She drives, you might have seen her around town because she's like an 80-pound redhead. And she drives this huge yellow car, so she drives it like this, you know. So the steering wheel's like up at her nose. And she told me one time, she said, well, dear, I don't understand how gasoline works, but I know it does because one time I ran out of gas and my car stopped. So there you go. That is just an absolute truth in the universe. So even people who don't understand the entire process understand the idea of the second law of thermodynamics. So you can do better, you can do worse, but ultimately you are going to use gasoline no matter what. So here's an idea. Let's talk about some other things about, and I have a little mathy thing I'll show you before we get into some of the guts of this. Here's another thing. If I have my coffee cup, I drink all my coffee, and I make a decision, a bad decision, to throw my ceramic coffee cup against that back wall, assuming I have the arm strength to do so, which I actually don't. But let's just say I actually hit the wall. What's going to happen to my coffee cup? It's going to shatter. Into how many pieces? 1 billion pieces. That is correct. So then if I recognize, let's say I put in 5 joules of energy in order to throw that cup. Okay? If I go to the back of the room and pick it up and put 5 more joules in energy into throwing it back to where I had it originally sitting, what are the chances it's going to reassemble into a coffee cup? Zero. That's exactly right. It's not actually zero. There is a 1 in 60 gazillion chance that me doing that is going to put it right back up onto the table in the coffee cup, but I'm not going to be waiting around to see that happen. So what that means is that if I take my coffee cup and I break it, and then I take a broken coffee cup and I reassemble it, I have to put more energy back into it than, in other words, it's not a zero-sum process, is it? It takes more to just get back to where I used to be. And that's what entropy is all about. It's tied in with the idea of no process. We'll say, therefore, if I could really do that, if I could do either of those things, break my coffee cup, reassemble my coffee cup with no net energy, or drive my car uphill into the headwind, drive my car downhill with a tailwind, and have the gas that I use for that whole process be zero, those would both be totally reversible processes. And neither one of them is. So the other upshot of the second law of thermodynamics that ties directly into this idea that all processes occur in a particular direction, no process is truly reversible. Now, this is not talking about energy. Energy is still conserved. So what we're really saying about energy is there's not just a quantity of energy, which is what we've talked about so far in our entire lives. There's also a quality of energy. There is some state that is more likely than another state. Some states of being, and I can use state in a generic sense, not like Michigan, but I mean like as in a way of existing. Some states are more likely than others. And that's how things exist. Now, every now and then you have an outlier. But overall, if you're going to make bank on something, you should bank on the more likely thing. So, and this is another interesting thing. This is also probably why the second law of thermodynamics is difficult for people to work with. Human beings are, all of us, me, you, everybody. Everybody is horrible at estimating risk. People are, for example, afraid of things that almost never happen and not afraid of things that happen all the time. So people think we just do this. It's built into our DNA. And there's an excellent book that if anybody ever wants to read it, we'll talk about why people do silly things psychologically. It's not just psychologically, but it's wired into our brains. It's called Deep Survival. It's by an author named Lawrence Gonzalez. I don't remember if it's, and it's not about the second law of thermodynamics, but what he talks about is how our brains are wired, especially in situations of survival. Like if you're off skiing somewhere and you get off the beaten path, your brain will tell you to do things that are really quite self-destructive, and why that happens, okay? And how we don't recognize the difference between being at a groomed ski resort and being off the trail 20 feet. You know, there are stories all over the place of people dying 100 feet from a ski lodge, or people snowmobiling through avalanche territory and just underestimating the incredible danger, you know? And we just do this. This is what we're wired to do, this because taking a risk blazes a trail for other people. And so in terms of communal living, the one guy who will go out and get himself killed blazes the trail for thousands of people to do something new and not get themselves killed. But anyway, that neither is here nor there. There's just a particular direction. Some states are more likely. Humans are bad at estimating risk. Okay? And we're also bad at estimating risk when it comes to money. It's not just your life, but humans are bad at estimating. And when I say risk, what I'm really talking about is how likely something is to occur. So let's just call it likelihood. Okay? Because we tend to focus on things that are less likely. For example, you know, I've been reading a little bit. We're talking about traveling. I get to go to London in May for a week. There were 4 people who were injured in a terrorist attack in London. And we had a conversation about whether we were going to go to London, and we're all bad at estimating risk, but we said, of course, we're going to go because, you know, it's fun and we got our tickets and everything. However, there's a lot more risks that are very much more real than getting killed in a terrorist attack in London, such as driving from here to the Billings airport. You know, that's probably the most risky part, or maybe not getting rolled in. I think we're going to go through Salt Lake. Salt Lake's a nice airport, but if you're going through like Newark, you know, your chances of getting robbed at the Newark airport are probably much greater than getting a terrorist attack in London. But those things stand out more. You know, one more person getting mugged in Newark is not that big of a deal in our minds, and yet it's a very real possibility. All right, so here's another one. Here's an example of something that you thought you were doing completely, but we were really only doing half of the problem. If you have water as either a steam or a liquid, what's going to happen? Is the steam going to turn to water, or is the water going to turn to steam? The real answer is that depends. What does it depend on? Yes, where you are. I mean, if you've got a pan full of liquid water and you put it on your stove and you put the burner on high, you're going to vaporize it. It's going to turn into steam. Okay? Now, if on the other hand, you have a big kettle full of steam and you pull it off of the heat, it's probably going to condense back into liquid. Now, not every particle. You're going to have some particles at the surface that statistically are just going back and forth seemingly in a random pattern. But overall, the macroscopic view is going to be one way or the other. Well, the reason I put this problem up is, and we'll discuss this a little bit more later on, but because in the past you did not know which way it was going to go. You knew intuitively, you did not know mathematically which way it was going to go. But you could tell. You could tell because you're like, if I put it on the stove, that means heat's going in. It's not a mathematical statement, but it's like, why else would I put it on the stove, right? You also know that if you take it and you sit a kettle of water here, that it will probably never vaporize. Nobody had to tell you that, you know? You can do a calculation just like this and say, how much heat do I need to come in to have my steam vaporize, and you can calculate that amount of heat. Doesn't mean it's going to happen. And that's the part that the first law of thermodynamics will not tell you. It tells you how much, doesn't tell you if it's actually going to go. And that's what the second law is going to tell us. So when you have steam to water or water to steam, you can see, do it the other way, we can make a calculation. We can also decide what the ambient temperature has to be in order for it to go in one direction or the other. So if the ambient temperature is higher than X, it will vaporize. If it's lower than X, it will not vaporize. But the first law of thermodynamics doesn't actually tell us that. Now, steam to water, water to steam is a relatively simple problem because we have an intuitive grasp of that. But if you have a process that's operating on a margin that's very close, or if it's a substance that you're not familiar with, you need some math to tell you which way it's going to go. So, for example, one thing that this relates to is the idea of a reaction rate. Okay? If you're in chemistry and you want to know how much of your products, how much of your inputs are going to form how much of an output, you absolutely have to know something about that process, and you may or may not. So that's what else the second law of thermodynamics talks about. So how many of you have in your life a refrigerator? I hope, except for James, maybe this summer you're not going to have one, but no, I know, well, that's right, or some summer, maybe not. Some summer, maybe not. I'm a fan of refrigeration. Refrigeration is awesome. And the thing that's most awesome about it from an engineering point of view is if you look at it on the surface, it makes no sense. Refrigeration makes no sense. How do you suck heat out of your refrigerator? How do you do it? Well, we know how. That's the good news, and we'll be privy to this as things go on. But if you think about, so man man discovered fire a long time ago, right? They didn't know how it worked, and you can use fire really, really well without understanding how it worked. So you take some contained space because catching things on fire is a bad idea, and you take something combustible and you light it up, and you get heat, and you also get light. This was a really interesting problem also because if you think about it, it hasn't been that long since electricity has run the world. But when electric light bulbs came out in the late 1800s, people were afraid of them. And the reason is that it was so ingrained in human existence to think about open flame and light being from the same source, that the idea of having a light that wasn't really, really hot was a strange thing. So one of the projects that Thomas Edison did seems really dorky now, but he had a parade where a bunch of men just marched in the parade with a band around their head and a light bulb on their head because he wanted to show people that you could put this light bulb on your head and you weren't going to catch on fire. Your hair wasn't your hair was not going to catch on fire. And that was a new concept for the human race. But heat and light came out of fire. We didn't really understand the way fire worked. We thought that it would release a substance called phlogiston, which is, and here is the rationale behind it. You take wood or you take coal and you burn them, and they used to weigh a bunch, and after you burn them, they weigh less. So therefore, there was something in there that was released, that released heat and energy, and that was called phlogiston. You can make a really good fire without ever knowing that that is incorrect. But what really happens is you release chemical energy, and you release carbon dioxide and water. Carbon dioxide, which tends to be, and sometimes other forms of carbon, we've talked about that a little bit, but basically they have weight, but they're gaseous, so they do not stick around. So that when you weigh the ashes of a wood fire, the ashes weigh less than the original logs left. But you didn't really release phlogiston. What you really did was you broke some chemical bonds and you released energy in the process of getting rid of these vapors. So you can do that. Refrigeration, on the other hand, works differently. Up until, really about 1900, there was the refrigeration as it exists today didn't really exist. And one of the main, there's a lot of different things, but basically food preservation. If you cool things down, food lasts a lot longer. And the other thing is the human condition of living. For example, has anyone here ever been to Phoenix? Yeah? It's what month? July. But that was pleasant, right?
It was just the airport.
And everything was, it probably felt really frosty cold. Do you know why? because they have air conditioning everywhere, right?
Oh,
I mean-
I was just on the tarmac.
Oh, I bet that was- oh,
Playing the planes.
I bet that was pleasant. Yeah, there you go. So, what were you saying?
So they have like misters.
Yes.
I grew up in Arizona. I didn't move to Colorado. Yeah, I didn't move to Colorado until I was a sophomore in high school.
So you know all
My
about
family's
this.
in Colorado.
So they have misters. Yes.
Yeah, like outside of like any kind of place you go outside, there's always misters. Misters
Yes.
all over. And
Isn't
we
that
have
cool?
like a hot, like you know, like there's like a too cold recess. It's
Yes.
like over like 120 we don't go to recess.
Yes. Well,
Or
and
117, 117.
that's the magic number.
That's the magic number. You don't go to
Okay.
How often did you hit that?
A good amount over summer. I mean, and
That's
even when it
fabulous.
wasn't there, like you didn't want to go on the wood chips. Like if you were to touch it, it was like a third-degree burn.
Right.
And you wouldn't like our recesses. Like you never went on like monkey bars or anything. Anything to do with the playground, our recess was completely different than anything.
So, isn't that amazing? So you know all about this. So,
It's stuck with you.
what's that?
It's stuck with her.
It stuck with you. Well, you know, they're just. I mean, I think that's wonderful. That's such a wonderful thing to start talking about it, and then you know, like we have friends that live in Phoenix. Well, they actually live up north, almost.
I lived
to-
in like the Chandler Mesa area.
That okay. So you live kind of south. Chandler Mesa is kind of
Yeah,
south,
south.
east-ish.
Yeah.
Okay. So we have people that live up by Glendale. So it's
Yeah,
kind of
I don't know.
okay. So kind of north, but we go there. We didn't get to go this year, but often we'll go there in February. And I'll tell you what, that area, the valley in February is the most beautiful place in the world to be. I mean, it's dry, it's pleasant. It's like the air feels like an extension of your skin. You know, I mean, but I've never been there in July, so congratulations.
It's
I've never
really
lived there.
dry.
Right.
Like, I've been to like Texas for like in Chicago for like basketball tournaments, and I think it was more brutal just because of like. The
Oh, it feels
humidity.
terrible.
Like it just feels like musky and stuff, and you don't get that feeling. It's
Right.
just really, really hot.
Yes.
But like you don't get that musky.
But you can
like,
still like get you can still get like heat stroke. I mean,
Yeah.
because it's kind of like when you're at a lower temperature, like if you're at 40 below zero and it's very still and very dry, it doesn't feel as cold as like, I mean, I went to school in Texas up by Houston, and it would get to be like 30 degrees, but it was so wet. I mean, it was just like moisture just precipitates out of the air. And I remember thinking, you know, I'm from Montana, I'm tough. I remember being down there in 30-degree weather and freezing my face off. You know, it's just like, it's horrible. You know, it's like, and I mean, back home, 30 degrees, you know, you just,
T-shirt.
yeah, exactly. You would wear, right, exactly. So,
What kind
but
of
so you're right.
preservation does that say?
Sorry?
What type of
Oh, food preservation.
Food.
So how did they preserve food? In other words, before they had, well, they put it on ice, which was classy. What's that? Cellars, right? Because cellars are
Salt.
colder. That's right, and salt, and lots of salt. That's exactly right. So food in the winter was not a really wonderful proposition. I mean, and this is really not that long ago. Really, up until maybe 120 years ago. I mean, you were pretty fortunate if you had the ability to eat something that wasn't like, well, beef jerky would be a good description of it, but really what, like salt, well, right, or like salt cod. They would take cod, you know, these big fish, and they would slice them up and they would salt them until all the moisture was gone in them, and then they would send them off. But I mean, when they did, and then you would rehydrate it in water. I wasn't alive in 1900, by the way. I've read about this. I know I'm older. I'm really old, but I wasn't alive in 1900. But they would put it in pots of water and reconstitute it. But basically, when you have cod like that, it looks like what comes out of your shoe. You know, like the instep, like if you were to take off your tennis shoe right now, the insole. That's exactly right. That's what it would look like. So, not really good stuff. So food preservation is huge, and that also contributes to health because, you know, people, if you look at pictures of people from that era, people got old really quick. I mean, 30 years old was, you know, a serious card-carrying middle-aged person, and 50 years old was like over the hill, and people retired at 65 because you were basically not able to do physical labor after about the age of 65. So people wore themselves out. Now we have another set of problems, but food is not one of them. So our food,
Yes, food is one.
yes, it's a different kind of a problem. That's exactly correct. So, but food preservation, to a point, promotes human health. And the human condition, like for example, in Arizona was one of the last states admitted to the Union, or to the United States. It was admitted in, I think, 1917. Hawaii and Alaska were 1959, and they were way late. But Oklahoma, Arizona, New Mexico were the last states in the lower 48 to be admitted. And one of the things about Phoenix was, until air conditioning, or they had swamp coolers, like you're talking about misters, but swamp coolers, which we don't really use too much up here, but they're just a wet heat, because air conditioning is actually a dry heat. But before air conditioning and swamp coolers, the population of the valley in Phoenix was about 30,000 people, and now it's millions and millions of people. But it is not really livable for a lot of people unless you have a way to moderate that degree of temperature. So, Jessica, I have a question for you, and you may or may not know this, being as you were a kid when you were down there, but I've heard, like, when people leave for the summer, they have to, like, drain their water or do something because, like, their toilets will blow up, or, yeah. I'm going to look into that. I just thought, Arizona, I'm going to have to ask you about this, because I'm like, oh, I don't really understand that, but it's like, I guess the water will boil out of there. I don't even know, but I mean, like, have to leave their air conditioners on. Of course, they let them go, they turn them up so that their house will stay at like 80 degrees or 85 degrees. But if you let your house get to 120 degrees, apparently it's not good for things in your house either. So anyway, but having never lived there, having only gone there in February, which is the right time to go to Phoenix, you know, I don't know. But that's what I hear. So anyway, refrigeration is backward. In order to do this, in order to create refrigeration, and we will discuss this in great detail as we go on, you need to move heat backward. You move heat backward, or against delta T. And in order to do that, how do you do that? By adding work. So once again, just like my friend Margie Scranton said, if you run out of gas, your car stops. If you unplug your refrigerator, what happens? It gets hot. That is exactly correct, because you're continually removing heat. The way that you're doing that is by running a compressor, which, like I said, we'll discuss later on. But there is no way that your refrigerator will continue to run, or will even stay at the same level of coolness unless you keep it plugged in, unless it's in a very cold room. All right, so what Chapter 6 talks to us about then is some different ideas. The first is that we're going to have two statements of the second law of thermodynamics. One of them is more applicable to heat engines, and one of them is more applicable to refrigeration. Oops, Clausius and KelvinPlanck. And these ideas are also tied in with the idea of reversible processes and
What's the second word behind Clausius?
Clausius Statement, STMT, and the KelvinPlanck Statement. Okay? And this is also tied into the idea of reversibility or irreversibility, and is also tied into the thermodynamic temperature scale. Which, what we know about the thermodynamic temperature scale so far is that there is a value of absolute zero, which we'll discuss a little bit more. So these are the ideas. Now, the first thing about reversibility, a reversible process or machine means that it is equally likely to proceed in either direction. So that means I have a cup of coffee sitting on the desk. It's equally likely that it will heat up as it is to cool down. When is that ever true? Never, ever. Every real process has a direction. Some things proceed in the direction very quickly. Some things proceed in the direction very slowly. An example of something that proceeds in one direction very quickly is any sort of an explosion. Okay, if you take a firework, set it on fire, boom, you release all the energy immediately. That's more irreversible than something that burns up slowly. But it's because you could stop at any point on something that's burning slowly and reverse it by putting in a little bit of energy. How hard is it to reverse an explosion? In other words, take a firework, blow it up, reassemble it to a firework. Well, it's basically impossible, right? Everything's all combusted. It's not impossible. It's just quite unlikely. So that's kind of the ideas that we're working with. So the two statements of the second law of thermodynamics that we begin with, and once again, these are conceptual statements, but basically the Kelvin-Planck statement says, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, this has to do with the idea of an exhaust stroke on an engine, but basically what it says is if I want to produce work and I have a boiler, for example, that I'm taking in heat, so I have a boiler, I'm doing something, I'm creating steam, I'm producing work. There's no way I can do that without exhausting some of my heat to the atmosphere. It just cannot happen, okay? Because if you think about it, there's no propulsion for this cycle to occur. Now, it would be a really cool idea to be able to take a boiler and take all of the heat that we make out of a boiler and turn it into work. But the Kelvin-Planck statement says it's not possible. Something is going to be wasted. Now, you could do a reburner thing where if this was still higher than the atmospheric temperature, you could take another little engine and make some more work and exhaust less heat, and you could continue doing that, and you could get a lot more heat out of it, but at some point it becomes less, it's always more efficient to do that from an energy point of view, but it becomes more and more expensive to get tinier and tinier amounts of energy. So there's a point beyond which it becomes an engineering failure to get more energy, okay? Because with engineering we have to consider everything. All right, so the Kelvin-Planck statement, and this is written, I'm just going to write in your book, it's on page 283. So the statement says, it's in the middle of the page, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So the piece that's left out of it is, if it receives heat from a reservoir, it has to eject heat to a reservoir as well. All right? And the Clausius statement, which has more to do with refrigeration, is on page 288. And the statement on the Clausius says, it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a higher temperature body. Okay? So here's my lower temperature body. That would be my refrigerator. To suck heat out of the refrigerator, I'm going to expel heat to the outside room, and in order to do that, I have to put in work. And if you take the work out, that means you've unplugged it, and this doesn't happen, and this doesn't happen. It just all settles out at the same temperature. All right, so those are both two statements about the direction in which things work. This is about moving heat, and this is about creating work. I'm going to put creating in quotes, because we're really just taking heat and exchanging it for work. All right, now also built into the Kelvin-Planck statement is the idea that if you can't use all of that energy from the boiler to create work, there must be some sort of equality. In other words, there's no reason that you can't write a first law statement that says all that heat becomes work. But when you put it into the second law, what you find out when you have all the heat produces the same amount of work, you find out that it violates the second law of thermodynamics, because what it's really saying is it's a reversible process. And what it's really saying is you could change it back from work into heat, and you could keep it going forever and ever and ever. So what's wrong? What is that called? Does anyone know what that is? When you, yes, perpetual motion machine. There's several different kinds of perpetual motion machines. The thing they all have in common is that none of them work. So you can put them on paper, but they never, ever, ever work. And they never, a third of them, one class of them does not work because it violates the second law of thermodynamics. Those are the harder ones to see. A perpetual motion machine of the first order is one that creates perpetual motion by ignoring friction. Second order violates the first law of thermodynamics. In other words, it creates energy. Third order violates the second law of thermodynamics because it's essentially reversible, which doesn't ever happen. Or violates the second law by having a zero increase in entropy, which is the concept that we have not mathematically discussed yet, but we will. All right, so the good thing that you need to remember is perpetual motion machines, none of them work. So sometimes I like to draw, I won't make you endure, but I like to draw a picture of Santa Claus and a picture of the Easter Bunny and a picture of a perpetual motion machine, because they all have something in common, which is none of them work. All right, so when we talk about this, then we talk about what kind of irreversibilities, and I think we're already pretty familiar with that. Any type of friction, any type of noise that's produced in a reaction. If you have a balloon and you blow it up, the noise is actually energy. Any light that's released, that doesn't happen routinely. Like if you have a bubble of acetone and you collapse it very quickly, it will actually glow a little bit for a second. And that release of light is energy. Anything like that is energy that's lost to the process itself. It's not lost in terms of conserving it. It's still conserved. It's just it's not going into a useful form. Okay? So, why do we talk about reversibility if there is nothing that's truly reversible? And the answer to that is reversible is an unobtainable standard we compare irreversible cycles or processes or whatever it is, we compare with irreversible. So in other words, sometimes we like to quantify how irreversible is a process, how much energy is lost to the irreversibilities of this process. And the comparator for a reversible process is what we call a Carnot cycle. Carnot is a person's last name. This fellow's name was Sadi Carnot. Sadi is the name that French guys think is a good name for a man, but that's okay. So Sadi Carnot was a civil engineer back in the 1800s, and he developed a theoretical heat engine, which is called a Carnot cycle. And a Carnot cycle then is the most efficient cycle, meaning that there are no internal irreversibilities, and so it depends only on external conditions, which even if you hadn't thought about it, kind of makes sense, doesn't it? I mean, if we're constrained by our environment in some way, like for example, if I have 110-degree coffee here and my environment's at 70, I'm only going to be able to lose heat at a certain rate, correct? If I have an engine and the temperature of combustion of gasoline is, I don't know, 170 or whatever it is, I have no idea what it is right now, I'm constrained by that. That's all the energy that I'm going to be able to get is how much is in that gasoline and how much I can combust. The other thing, if you think about it, if you have a higher temperature, outside temperature, your efficiency actually becomes less In other words, you can get less energy out of a cycle if it's a temperature-based cycle. Now, automotive engines are a lot more complicated than that, but you're constrained by how much energy there is because you cannot put your exhaust below ambient temperature. That doesn't even make any sense, does it? So all you have to work with, if it's 70 degrees outside, the minimum that your exhaust is going to come out at is 70 degrees. And that's actually would be an amazing situation. That doesn't actually happen. If you put your face on a tailpipe, you'll find out it's not really at 70 degrees, right? It's not a good temperature to put your face on. So
Yeah, first gust of exhaust.
I've seen people do the weirdest things. I know. So yes, but it's also not. And anytime that you have, like, if you think about this, if you have an exhaust cycle in any type of an engine that you have unspent fuel, that's a terrible, terrible inefficiency, right? So anything that comes out that's not carbon dioxide and water is an inefficiency of the engine. And anything that comes out above atmospheric temperature is, and above actually the pressure of the atmosphere as well, represents some amount of work that you could have got out of it in a theoretical sense. May not be practical, but in a theoretical sense, that's money that you left on the table, so to speak. Okay? So, the Carnot cycle only depends on the external conditions. And this is where the idea of the thermodynamic temperature cycle, or the thermodynamic temperature scale comes up. It turns out that for a reversible cycle, the ratio of heats taken from the high temperature reservoir and expelled to the low temperature reservoir is equal to the ratio of temperatures from the temperature of the high reservoir and the temperature of the low reservoir, if and only if T sub H and T sub L are in absolute units. In other words, we have to be on that scale where 0 Kelvin equals 0 Rankine equals absolute zero. And so this is actually the meaning and a very important consequence of the thermodynamic temperature scale. Fahrenheit and Celsius are based on zeros other than thermodynamic considerations, but 0 is a how would you put it? Well, if you think about this, if you were expelling to 0 degrees absolute, this ratio would go to infinity, wouldn't it? So what does that tell you? Well, that tells you that you would be able to suck all of the heat out and that the heat would be infinite. So what we do is we have an asymptotic approach to 0 degrees Kelvin or 0 degrees Rankine that represents a theoretical limit of some sort. And once again, there's a lot of myths about what absolute zero means, but what it really means is that at absolute zero, the entropy of a perfect crystalline form of a material is a minimum. So it appears to be something that we cannot surpass. We haven't really even attained it. We've gotten fractions of a degree above absolute zero, but if you think about it, how do we make things colder? Like if you have a bottle of water and you want it to get colder, how would you make it colder? Put it in contact with something colder yet. So if nothing's below absolute zero, how do we ever get anything to absolute zero?
How much is still unexplained by science?
Oh, you mean like in general? Like nearly everything.
Yeah,
right?
I mean, we have all these things like thermo and mechanics and all these rules and ideas and
right.
concepts.
Yes.
How
Well,
much more do we have no concept of?
Well, this is a great thing to bring up here because since you are all budding scientists, and some of you are beyond budding, but to think about the world in a scientific way. Science examines what science examines, and what it doesn't examine is not examined, and you really can't draw correlations to it. So I think what you've identified, James, is a very important idea. It's like, let's talk about global warming for a minute, okay, or temperature change. We have studied scientifically several of the mechanisms that contribute to changes in ozone, which is a statistical phenomena, which ozone is O3. As you know, oxygen usually occurs as O2. There's some changes in its ability to transmit energy in the form of heat, and we've studied those mechanisms, and we know that carbon dioxide production affects those mechanisms in certain ways. Those are the things that we know scientifically. We also know scientifically that if you examine the temperature of the Earth over the last 120 or 150 years, that there have been some significant changes to the temperature of the Earth. So that's what science knows. The harder thing, which is not really a scientific correlation, I'm not saying it's inaccurate, I'm just saying it's not necessarily scientific, is if you take this body of knowledge, which is how CO2 affects ozone, you take this body of knowledge, which is how ozone transmits temperature, and then you take this body of knowledge that says the temperature of the Earth, and you try to put them together in a big meta thing, it may or may not be correct. Okay? So science studies what it studies. So if you haven't studied it, you don't know it scientifically. So that's an important concept. So, and you know, so why, like for example, there's some other things too. So when you guys, to me, engineering is like the best of the best because it brings everything together. You know, I mean, you're not just studying math, you're not just studying chemistry, you're not just studying physics. You're not just studying the regulatory environment, you're not just studying politics. You have to think about, and you're not just studying, you have to bring it all together to come up with a good solution. So, and that's what we do in engineering, we find solutions to problems. So if it's something is a solution in one area, it may or may not be a solution 10 degrees off of that. For example, if you think about byproducts of nuclear energy, if you were a pure scientist, if you were a nuclear scientist and you just think about nuclear energy is awesome because we can take this little tiny plug of a radioactive material and we can turn it into a bazillion kilojoules of energy, and then we can run everything for almost free. That is true. What else is true about nuclear energy? Everything that touches, first of all, you don't just run it from this little pellet of radioactive stuff. You had to dig up acres and acres and pits of stuff to find and purify this little tiny bit of stuff, right? So there's that. There's also the fact that everything that comes in contact with that very concentrated radioactive material now is radioactive and will be radioactive for hundreds of thousands of years. And that's just the way radioactivity works. So you have to weigh the benefits against the I would say detriments, but against what it's going to cost you to do it, not just in a monetary sense. It's why, and here's one problem that's solved. Where is one application on Earth where we use nuclear power very efficiently? Does anybody know? Yes?
Aren't a lot of like aircraft carriers and stuff?
Yes, absolutely. Anything in the ocean runs very well on nuclear power. Why is that?
Because your coolant is all around.
Your coolant is all around you and the ocean is really, really big. So if you have 1,000 nuclear subs running in the ocean, it's still not going to significantly change the temperature of the ocean. And the supply of water around you is basically inexhaustible. If you think about like back when, what year was it, 2011, when the Fukushima disaster happened in Japan, you know, they thought they had a flawless delivery system for water. And water has that really high specific heat, which is why you always have to have this incredible supply of water in order to do nuclear energy, because you've got a lot of heat that you have to dissipate, or else it starts to melt your equipment, which is bad because all of your equipment is radioactive. So having it melted is bad. So I write that down for notes, right? But anyway, so bad radioactive nuclear uncontained situations. So you have this situation then where you think you try to, you know, there's this idea in engineering that is never really true, but we go for it all the time. When you have something of high risk, you try to make it fail-safe, which means you don't just think about it one way. You think about it 65 different ways, and you try to have redundant systems in order to make it not fail, okay? So fail-safe, like when you build a new building, for example, you want to have multiple ways for people to get out. You want to have sprinkler systems so that if a fire happens, that the sprinklers will put out the fire, and you have to have multiple ways for people to get out. Back in the old days, they had fire escapes, and people would routinely, be in very tall buildings, and they get on a fire escape, and the fire escape would pull out of the bolts in the wall, and everybody would fall to the ground and die. So it's a bad idea. You have to have backup plans. Elevators are not good backup plans for fires. Why is that? First of all, you're trapped, but second of all, what happens in an elevator shaft? Yeah, it's a chimney. Exactly. It's a chimney with you in the middle of it. So this is a bad thing, right? So you have to have all these different ideas. So these are just some of those ideas. But so nuclear has some really positive things and also has some very negative things. And so in order to use nuclear power, you have to weigh those things against each other. And right now, we're not talking about nuclear in this country very much, but we're talking a lot about burning hydrocarbons, and because of this effect in the ozone. And I don't know. I mean, what happens if we don't I'm not saying, I'm just going to throw this idea out there. What happens if we don't have power? What starts happening to civilization? Well, people start freezing, and their food starts spoiling, and they stop having clean water, and all kinds of stuff. So it's always balancing those kind of things out. So anyway, so that kind of answers, I hope, your question. What do we know about absolute zero? We know what we've studied about it, and there you go. So we try to study everything about a certain thing before we make decisions, but we don't know anything that we don't know. We don't know anything that we haven't studied. All right, so what does a Carnot cycle look like? Well, a Carnot cycle it's usually, and there's two different ways, but we can have a Carnot cycle for a heat engine, or we can have a Carnot cycle for a refrigerator. But let's talk about a heat engine first. And basically, it operates in a cycle, which means that we do not spend our working fluid. So one thing, if you think about like a car engine, when you have gasoline and you create a flame front and you raise a piston and it makes the drivetrain work, you exhaust that gasoline and you need more gasoline. Cycles work in a way that the working fluid is not exhausted. And you can approximate non-cycles with cycles sometimes. But like I said, the big thing you need to know is this is the most efficient, and we use it as a standard of comparison because of that. So even though it is theoretical, it is a standard comparison that's based only on the conditions surrounding the heat engine. So what we basically do is, this is the equivalent of a stick figure to a Carnot heat engine. You want to get work out. How do you do that? You get that by putting heat in, and the second law of thermodynamics tells us that means you have to expel heat. So what that means is that you take in Q sub H at some high temperature, you expel Q sub L at some low temperature, and the way that it looks is that every stroke, it's a 4-stroke, 1, 2, 3, 4, and every stroke is reversible, and some of them are expansions, 2 of them are expansions, 2 of them are compressions, 2 of them are adiabatic, and 2 of them are isothermal. So basically you start with a reversible isothermal expansion. We'll talk about these a little bit in detail. Then you go to a reversible adiabatic expansion. Finally, you go to reversible isothermal compression and a reversible adiabatic compression. Okay, so if we go back to my engine, since I'm taking in heat here and expelling heat here, these two cannot be adiabatic, can they? Because adiabatic means Q is equal to 0. So these two are my adiabats. So that leaves these to be what? If they're not adiabatic, What are they going to have to be? Isothermal. And that's what we say right here. So this is isothermal, and this is isothermal. This is adiabatic, and this is adiabatic. So if I have an isothermal expansion, that means that I'm going to increase my volume. And so what ends up happening is that this is going to be my isothermal expansion. And then I'm going to have an adiabatic expansion, an isothermal compression, and an adiabatic compression, taking me back to the same set of conditions that I had to begin with. All right? So this is also called the power stroke, heat intake stroke, exhaust stroke, and this is just the place that gets you from point A to point B. Sometimes there's a mechanism here. You could have a valve or a just anything. You could, well, in real life, you're going to end up having to put a little bit of work in here often, but in a pure Carnot cycle, that's not going to happen. So if we draw this on a pressure volume diagram, what we find is that when we go from point 1 to point 2, and I'm just labeling this the way that your authors label it, we have Q sub H going in, so that is at T sub H. Then when we go from point T to point to 3 to 4, if this is T sub H, this must be T sub L, and this is Q sub L, right? Then from here to here, we drop our temperature from T sub H to T sub L, and here we raise our temperature from T sub L to T sub H. And the area here, because we know since work is equal to the integral of P dV, one interpretation of that is the area. And so the area bounded here is equal to the work output.
The one that's coming out on the left, is that?
Here?
Yes.
Q sub L. That's just my exhaust stroke.
Okay.
Yeah. And these states, each of these strokes is defined on page 298 in your textbook. Right?
Well, what does that say you're pointing at?
Page 298,
No, what you were pointing at in the middle of the square.
area equals work
Area.
because of this integral. All right? So, here are some ideas. If we have a T sub H reservoir and a T sub L reservoir, a Carnot cycle is the most efficient cycle that can operate between those two temperatures, meaning any real cycle will be less efficient than a Carnot cycle given those same two temperatures of the reservoir. And it also turns out, we're going to introduce this without proof. The proof is interesting, but takes a little bit of time, is that any reversible cycle can be duplicated by a series of Carnot cycles, or a Carnot cycle can be replicated with a series of other reversible cycles. So reversible equals, mathematically, Carnot equals the best in terms of efficiencies. Okay? Real equals irreversible equals not as good in terms of efficiency as a Carnot cycle. All right, so I talked about the idea of the thermodynamic temperature scale. So the last little piece of information I'm going to give you today is 610. If you look at this heat engine, well, this is how much heat we're putting in. This is how much heat we're rejecting. So we can say that in general, for this type of a heat engine, that the work is going to equal Q sub H minus Q sub L. All right, and the efficiency of a cycle, which is defined by the variable NTH, which stands for thermal efficiency, is going to equal how much we get out of what we want, which is work, over what we have to pay for, Q sub H. That's the amount of heat that I put through the boiler, or the wood that I'm burning, or the coal, or the nuclear fuel, or whatever, in units of energy. I've just defined that work is equal to Q sub H minus Q sub L. So I can say that the efficiency of any type of a cycle is Q sub H minus Q sub L over Q sub H. And if I divide each one of these terms through by Q sub H, I can write this as Q sub H over Q sub H is 1 minus Q sub L over Q sub H. So this is a general statement of the efficiency of a heat engine. Now another thing that you can look at is Q sub L is always going to be less than Q sub H, isn't it? In other words, you're always going to expel less heat than you put in, because otherwise where would it have come from? You didn't put it in, it's not there. So this fraction is always going to be somewhere between greater than 0, because otherwise Q sub L would have to be 0, meaning I don't have an exhaust stroke at all. So it's going to be greater than 0, it's going to be less than 1, so that the efficiency is always going to be greater than 0, less than 1, or less than 100% if you prefer. Now for a Carnot cycle, because of that relationship that I showed you, that a Carnot cycle being the most efficient nth of a Carnot cycle, I can also say that it's equal to 1 minus T sub L over T sub H. Now this is only for a Carnot cycle. This is for Carnot cycles and real cycles. So this is general.
So is a Carnot cycle always 100% efficient?
It is not. It is never 100% efficient. It's the maximum efficient, whatever that number turns out to be, and it turns out it's dependent upon the temperature of the intake reservoir and the temperature of the exhaust reservoir. Okay. But if you have a Carnot cycle, you can use both of these relationships. If you have a real cycle, you can only use this relationship. And trust me, you will try to use this with a real cycle, because everybody does, because it's such a cute equation. But can't happen. All right, so that gets us through section 6.10 today, which is pretty much the only other thing I really need to do is to talk to you about Carnot refrigerators, which will just take a little bit. So is today Tuesday? Thursday, we'll come back and we'll finish off chapter 6. Give you some homework. That'll be it. All right? And so then that puts us at the following week, of course, is advising day, and then we'll have our exam on the next day. So sometime, we'll do a little review next time as well. Yes?
Your advising day sheet real?
It is. And there's lots of spots still, so.
So the sophomores, do we still need an advising day?
If you're going elsewhere, unless you need help like with your transfer issues, which I can help you anytime. It doesn't have to be on advising day. So, but yeah. So if you're transferring, you don't have to come see me. But if you're not transferring, come see me. Yeah, there you go. That's the answer. So, all right, stop and streaming.